is the third lecture on Bessel differential equation. In the earlier two lectures, we have introduced Bessel differential equation and performed its singularity analysis and obtained the series expression for integral as well as non-integral values of the parameter. And to be specific, we have obtained Bessel function of few low orders, as for example J0, J1, J of half, J minus half, etc. Today we shall discuss the generating function of Bessel differential equation, Bessel function of integral orders. So the generating function for Jn of x, where Jn of x is Bessel function first kind and of integral order That is to say, the discussion that we are going to make under the heading of generating function is applicable only for Bessel function of integral orders. Recall that for integral order n, Jn, the series expression for Jn is summation over k is equal to 0 to infinity factorial k plus n factorial minus 1 to the power k x by 2 to the power 2k plus n, and we have j of minus n of x is equal to minus 1 to the power n jn of x. This we know from our earlier discussion. Now we consider the function g of xt as e to the power x by 2 t times 1 by t, and our aim is to show that this is equal to n from running from minus infinity to plus infinity t to the power n jn of x. Remember always that n belongs to integer. This expression is not valid for fractional order of Bessel function. To prove this, we start with the left hand side, that is g of xt is equal to e to the power xt by 2. I think front side has to be increased a bit. E to the power xt by 2 e to the power minus x by 2t, and expand both of these in Maclaurin series. For the first one, the Maclaurin series expansion is r ranging from 0 to infinity, x to the power r, t to the power r, 2 to the power r factorial. And the for second one, it is s running from 0 to infinity, minus 1 to the power s, x to the power s, t to the power minus s, and 2 to the power s, and s factorial. So sum over r and s, minus 1 to the power s, and then x to the power r, x to the power, or rather we write it t to the power r minus s, t to the power r minus s, r factorial, s factorial, and then we have x and x by 2 to the power r plus s. This is s. We introduce n is equal to r minus s, so that the sum over n, if we perform a sum over n, then sum ranges from minus infinity to plus infinity, because for a finite n, as s goes to infinity, n goes to minus infinity, and for a finite as when r tends to infinity, n tends to plus infinity. And we want to replace r, so r is equal to n plus s, and there is a factor r plus s, so r plus s is equal to twice s plus n. So this becomes sum over n and s minus 1 to the power s. Sum over n, we write t to the power n, then sum over s from 0 to infinity minus 1 to the power s. This part is 1 upon s factorial, and then s plus n factorial x by 2 to the power 2s plus n. This part, the quantity within the s summation is simply jn of x, so this is equal to t to the power n jn of x, and n ranges from minus infinity to plus infinity. So this is the generating function for Bessel differential equation. The generating function of Bessel differential equation has few important application. We shall show the application one after another. First thing is what is known as addition theorem. That is, if we have two arguments, two quantities, variables x and y, and we want to express Bessel function of a particular order of argument x plus y, this can be done as a combination of Bessel function with argument x and a Bessel function of argument y. This is known as addition theorem. So applications of generating function, one is addition theorem. We consider g of xt is equal to e to the power x by 2 t into 1 upon t. This is equal to sum over n t to the power n j n of x. We consider another generating function g of yt. This is e to the power y by 2 t minus 1 upon t, and this is equal to sum over m ranging from minus infinity to plus infinity jm of y. We multiply this, so these two, so g of xt go multiplied by z of yt gives you e to the power x by 2, e to the power x plus y by 2 t minus 1 upon t on the left hand side when this and these two are multiplied, and on the right hand side we get sum over n and m, both ranging from minus infinity to plus infinity, t to the power n plus m jn of x jm of y. And if we apply the generating function on this can be written as summation over L from minus infinity to plus infinity t to the power L jl of x plus y is equal to this thing. Now this is an identity in T. So a particular power of T, if we equate the coefficient of a particular power of T on the other side, either side, we get a relation involving j of Bessel function of first kind with argument x plus y, with Bessel function of first kind with argument x multiplied by argument y. So the coefficient of t to the power k gives j of k x plus y is equal to, from right hand side we make a, if we make a sum over n, then this is Jn of x and j of k minus n of y, because the t to the power k from left hand side comes for when L is equal to k, and on the right hand side k n plus m is equal to k, so the sum of the order must be the same, and you can write it also as sum over n j of k minus n of x j of n of y. This is known as addition theorem. That is the right hand side. If we have on the right hand side Bessel function of argument x and y, and on the left hand side we have Bessel function whose argument is the sum of the arguments of the Bessel function on the right. That is why it is known as addition theorem. Now we come to Jacobbi identity. As the second application of Bessel function, we will derive Jacobbi identity. It is an interesting result involving Bessel functions. There are various varieties of Jacobbi identities involving Bessel functions available in the text, but here we shall cite only a simple one. The application Jacobbi identity, or Jacobbi series, rather it is Jacobbi series. In the generating function we put t is equal to I, so that 1 by t is equal to minus I, and the generating function g of xi becomes e to the power x by 2 I minus or minus I, so it is e to the power ix. And on the right hand side we have summation over n ranging from minus infinity to plus infinity I to the power n jn of x. We write the left hand side as cos x plus I sin x, and on the right hand side first n is equal to 0, so I to the power 0 j0, I am omitting the argument is x all alone. Then we have I to the power 1 j1 plus I to the power minus 1 j of minus 1. This is the contribution when I is equal to plus minus 1. Then we have I square j2 plus I to the power minus 2 minus j2 I cube j3 plus I to the power minus 3 j of minus 3 plus I to the power 4 j of 4 plus I to the power minus 4 j of minus 4, and such similar things. This is simply j0. Now you consider this. This term is 1 upon I, this is minus I, and j of minus I is equal to minus 1 to the power 1, j of 1 is equal to minus j1. So these two minus sign makes it positive, so we get twice I j1. This is the contribution from this term. Now coming to this term, I squared is minus 1, this is 1 by minus 1, this is again minus 1, and j of 2 j of 2 and j of minus, so this is I squared is minus 1, this is minus j2, this term is minus j2, and this is minus of minus j2, but this is equal to j2 because of this relation. So this is equal to minus 2j2. So this is minus 2j2. This is the contribution for n is equal to plus minus 2 term. Then this term, this is minus I. This is minus ij3, and this is 1 upon minus I. So plus 1 upon minus I, and this is minus j3. So this, when this comes on the numerator, I comes on the numerator, this becomes plus and this is minus. So this is minus twice ij3, altogether minus twice ij3. And coming to this term, so this is the contribution of this term, and this is a plus and this is also plus, so we have twice j4 and other terms. So if we write the real part, it is j0 minus twice j2 plus 2j4, while obviously the next term is minus 2j6, like this, plus I times twice I times j1, then minus j3 plus j5, and so on, so term. So this term we identify with the cos x, and this term we identify with the sin x. So we write cos of x is equal to j0 of x minus 2 j2 of x minus j4 of x plus j6 of x. You can write here, put it in a using a summation symbol, and for sin x twice j1 of x minus j3 of x plus j5 of x, and so on and so on. Either one of this expression is known as Jacobbi search. As the third example of the generating function, we shall derive recurrence relation. Before going to recurrence relation, I want to point out that there are other versions of Jacobbi series in connection with the Bessel function available in text. To be particular, if we put t is equal to e to the power I theta, which leads to the integral form of Bessel functions, but the mathematics involved, mathematics required is a bit involved, so I am refraining myself from going to the integral representation for the Bessel function using Jacobbi search. Now that the third example, we consider the recurrence relation. So as we are aware of the recurrence relation from our earlier studies on legendary Hermite log polynomials, that if we differentiate the generating function once with respect to the parameter t, we get a relation involving special functions of different orders, and if we differentiate the generating function partially with respect to the argument, then we get a relation involving the derivative of the special function and the special function itself of different orders. So we differentiate first this generating function partially with respect to parameter t. So we write del g del t. So as this is the expression, so we get x by 2, the things which is again g of xt, and then we have del t of t minus 1 upon t. So this is equal to x by 2 g of xt, and this part is 1 plus 1 upon t square. And on the right hand side, when we differentiate this, we get a summation over n t to the power n minus 1 jn of x. So for g we write another expression of this sort. So we have 1 plus t x times 1 plus t square, or write it as 2. Then this part we write in summation over m jm of x. This is 1 t taken common in the denominator, so it is 1 plus t square. 1 plus t square is multiplied with this, and for g of xt we write this expression, and the other thing is 2 by x times t square multiplied to this. So sum over n t to the power n plus 1 jn of x. Let me describe the simplification once again. This is the generating function. I am differentiating it partially with respect to t. So the left hand side gives x by t, g of x itself, and this, which is this part. And when we differentiate right hand side partially with respect to 2, the result is this. This part is simplified as 1 plus t square by t square. This by t square is multiplied with this term, so the power becomes n plus 1, and this is the simplification, and x by 2 term has been adjusted here. So the coefficient of t to the power k, being a identity, the first term contributes to when m is equal to k. So this is xk jk of x, and this term contributes when m plus 2 is equal to k, that is j of k minus 2. And on the right hand side we have 2 upon x, and this contributes to x to the power k when n plus 1 is equal to k, that is n is equal to k minus 1. Replacing k by k plus 1, we get j of k plus 1 of x minus k plus j of k minus 1 of x. This is 2k by x jk of x. Since the generating function, the relation of generating function holds for Bessel function of integral order only, this derivation is valid for integral values of k. Later on we shall show that this relation is also valid when k is non-integer. Before going to the other recurrence relation, I want to apply this for the evaluation of few low order the Bessel functions. So we put firstly k is equal to 0. If we put k is equal to 0 in this equation, then we get j1 plus j of minus 1 is equal to 2 by x. Sorry, I put j is equal to 0. So If we put k is equal to 0, the left hand side gives j of plus 1, this is j of minus 1, and on the right hand side this is 0 as k is equal to 0. So left hand side is 0 and right hand side is 0 because j of minus 1 is equal to minus j of 1. So this relation is nothing with k is equal to 0. So we try with k is equal to 1. With k is equal to 1 we get, this is j2 of x, I am not writing the argument, this is j0, and on the right hand side we have 2y, k is equal to 1, 2 by x j1. So we can write j2 is equal to 2 by x j1 minus j0. We can use k is equal to 2 to write j3 in terms of j3 in terms of j1, j2, and we can replace j2 in terms of j1, j0. So we can in principle derive all the higher order integral orders of Bessel function of first kind in terms of j1 and j0. So this is for k is equal to 2, we get j3 plus j1 is equal to 4 by x j2, or j3 is equal to 4 by x j2 minus j1, and we can put the value of j2 over here, 4 by x, and for j1 we write 2 by x j1 minus j0 minus j1. So it is 8x square minus 1 j1 minus 4 by x j0. Let me first check the relation. Okay, this is the, in this way we can develop Bessel function of higher orders. We write this relation, the basic recurrence relation is j of k minus x plus j of k plus x is equal to twice k by x jk of x. This is one generating function. Now the other generating function is obtained when we differentiate the other recurrence relation is obtained when we differentiate the generating function partially with respect to the argument, and in that case we shall get a relation involving j prime. So del g del x is equal to 1 upon 2 t minus 1 upon t at g of xt, and on the right hand side we have summation over t to the power n j n prime of x. So we take t common, so t common in the denominator, this is t square minus 1. So this is t square minus 1, and for this we write summation over t to the power m jm of x, and in the denominator we have 2t, so 2, this is if we collect the coefficient of t to the power k or again, so first term contributes with m plus 2 is equal to k, so m is equal to k minus 2. The second term contributes when m is equal to k. And on the right hand side we have this n plus 1 is equal to k, so n is equal to k minus 1. As usual, as in the earlier case, we replace k by k plus 1, so we get j of k minus 1 minus j of k plus 1 is equal to twice jk prime. So this is the other recurrence relation. So we write this relation J of k minus 1 of x minus j of k plus 1 of x is equal to twice j k prime of x prime is ddx. We can use this relation to find out the derivatives of Bessel functions. As for example, we put k is equal to 0 here. This relation with k is equal to the second recurrence relation with k is equal to 0 gives j of minus 1, and then this is minus of j1 is equal to 2j0 prime, and since this is minus 2j1 twice j1, and we can put other values 1. If we put k is equal to 1, then we get j0 minus j2 is equal to twice j1 prime. We can replace j2 in terms of j0, j1, and this is j0 minus j1. j1 we have worked out, j2 we have worked out just a little bit earlier, is 2 by x j1 is equal to 2 by x j1 minus j0. And on the other side we have twice j1 prime. So these two cancels out, and we 2 cancels out, and we get j1 prime is equal to minus j1 by x. These are the two recurrence relation and their application. We can use these two relations to get other important relations too. So we add these two equations. We call equation this one A and this equation B. We just add these two. So on the left hand side we have j of k minus 1, j of k minus 1. On the right hand side we have k by x jk plus jk prime. We multiply both the sides by x to the power k, and we get this is k x to the power k minus 1 j of k plus x to the power k jk prime. This can be written as ddx of x to the power k jk of x. The first term is k x to the power k minus 1 jk, and the second term is this. So this is one relation. If we integrate this between the limits 0 to a, then integrating we get 0 to a, integration becomes x to the power k j of x is equal to integration from 0 to a x to the power k or we can write as integration x to the power k jk of x dx 0 to a. You see that the lower limit is nothing, as Bessel function of first kind is finite at the origin. So it is simply a to the power k jk of a. This is very important relation involving Bessel function of first kind. So we write the relation as integration x to the power k jk of x dx from 0 to a to the power k j of k minus 1 of a. Now if we subtract b from a, then we get so a minus b gives us j of k plus 1, j of k plus 1 of x is equal to k by x, j of k of x minus we multiply both the sides with x to the power minus k. So we get on the right side we get k times x to the power k minus 1 jk of x minus x to the power minus k jk prime of x. This is minus dd x of x to the power minus k jk of x. If we differentiate first term, this is minus k times x to the power, this is k plus 1. You get this term. And from second term we get this. So again, if we integrate it, then we get integration 0 to a x to the power minus k j k plus 1 of x dx is equal to minus this is the other important relation we can obtain from generating function. In the next class, we shall show that here the relation has been derived from generating function, which is valid only for Bessel function of integral order. So to say, the derivation that we have made in this class is valid only for integral orders of Bessel function. So these relations are valid only when k is equal to integer. But in the next class, we shall derive the same relation from the series expansion of Bessel function of any arbitrary order, not necessarily integral order, and we shall arrive at all this relation where k is replaced by alpha, where alpha can be integer or non-integer as well, and we shall show that this relation are valid even for non-integral order of Bessel function. That will be our topic of discussion in the next class.